Hi everyone. Section 1.11 is an optional introduction to derivatives in calculus. Now remember, when we were talking about slopes of secant lines and average rates of change, we looked at this difference quotient, rise over run. F of B minus F of A all over B minus A, rise over run. Now let's say that instead of the constant B, let's consider the variable X. We'll let X change, but we'll let A stay fixed. So we have a variable right endpoint over here. Now let's say that I want to know the instantaneous rate of change at A. That's going to be the slope of this tangent line. And that's going to be the derivative, the slope of this tangent line. So how do we get the slope of that tangent line? We go through this limiting process. So at x equals a, consider the corresponding point a f of a. And then consider this sequence of second points along the graph as the x-coordinate moves towards the a-coordinate, either from the right or from the left. Consider the sequence of secant lines. Each secant line has a slope. And the idea is that as x approaches a, we often do use arrows in calculus, as x approaches a, the slopes of the secant lines will approach the slope of the tangent line. Slopes of secant lines will approach the slope of the tangent line here. And the slope of the tangent line is called the derivative. The derivative of f at a. Which is often denoted by f prime of a. The derivative of f at a, that's the slope of the tangent line at x equals a. The slope of the tangent line that touches the graph at this point. And the idea is that this tangent line is going to be the best linear approximation to this graph near this point. F prime of a, the derivative of f at a, is the slope of the tangent line to the graph of f at the point a f of a, if that slope exists. If we get a vertical tangent line, the derivative does not exist. Sometimes, like for absolute value, there's a mismatch of slopes. There's no derivative at x equals 0. If f prime of a exists, we say that f is differentiable at a. There is a single tangent line, and it's not vertical. Like over here, we have a single tangent line, it's not vertical, and it works from both sides, from the right and from the left. So here's one way to define a derivative. You take this difference quotient, rise over run, f of x minus f of a, all over x minus a. Let's say this is the x-coordinate here. We take the limit as x approaches a. So if this is the slope of the secant line, we want to know what the slopes approach as x approaches a. Another way to look at this, going all the way down here. We've seen this before, rise over run, where this is really focusing on the run. The rise is f of x plus h minus f of x. The run is just h. Rise over run. And we take the limit as h approaches what? To get the slope of the tangent line, we take the limit as h approaches 0. So h values could be positive, h values could be negative, but either way, they're approaching 0. The run. F prime of x, the derivative at x in general, is the limit of this difference quotient as h approaches 0. This is the limit definition of the derivative. It's perhaps the most famous form. And you can think of the derivative function as a slope function. For example, here's y equals x squared. The derivative function is given by y equals 2x. So the value of 2x, the y-coordinate on the green graph, gives the slope of the tangent line to the red graph. At x equals 0, 2x equals 0, the y-coordinate on the green graph is 0, so there's a horizontal tangent line for the red graph. When x equals 1, 2 times 1 is 2. That's on the green graph. The point 1, 2 is on the green graph. The slope of the tangent line at x equals 1 on the parabola here is 2. So again, the y-coordinate on the green graph gives the slope along the parabola. The y-coordinate, the 2x value, gives the slope for the graph of y equals x squared.